Oh, yeah.
All right, here we go. We're going to take a look at number 26. And I know you're all excited about starting first period, but we need to kind of be quiet a little bit so that everybody can see what's going on. All right, so we're going to graph this. Now, those of you that are new to us, do not panic. Pay attention, write it down. You will get it figured out, don't worry.
Were you this close last year?
All right, so here we go. We're going to graph a secant. All right? What is the very, very first thing we think about when we graph a secant?
The reciprocal.
The reciprocal. So we're not even going to graph the secant. We're going to start by graphing the what? Cosine. Very good. So we're going to start by graphing this. Okay. Now, all of us need this review. What does this negative do? Flips it. So we've got memorized that this is one period of the cosine curve, right? But we're turning it upside down, so the picture I draw is actually going to look like that, right? Now, you see any additions or subtractions in the problem? Why no? What does that mean if there's no adds or subtracts?
No.
We haven't shifted it anywhere. So we are actually going to draw that picture. That's what we're going to draw. And how high and low are these waves going? 2, because of this guy right here, right? So it's upside down because of the negative, and we're going up and down 2. Okay. Where's this thing end? What's this label out here?
4 pi.
We need to know our period, right? And what is the period of a normal
2 pi.
cosine curve? 2 pi. In fact, the period of everything is 2 pi except what?
Tangent.
Tangent and cotangent. And what's the period of the tangent and the cotangent?
1 pi.
1 pi. Very good. So the normal period is 2 pi, but this one has been divided by a half. Remember, groupies, this coefficient, the coefficient on x, divides the period. Always. So 2 pi divided by a half, 4 pi. So this label is 4 pi. What's the midway point then, right here in the middle? 2 pi. What's the midway point of these?
Pi.
Pi. And this one would be 3 pi. You are finished with the cosine. That is a beautiful cosine curve. Delaney, you with me so far? Yes. Now, I have to make it a secant. And that's real easy, isn't it? All I have to do is drop in some asymptotes and flip the curves. And the asymptotes get dropped in at the zeros. Wherever you cross the x-axis, is where you put an asymptote. And then you take the hills and flip them up. And you take the valleys and flip them down. And this one looks a little strange because it's only half a valley. If you were to continue the valley, you'd have the whole flip. Here's another half valley. Oh, it flips down like that. The purple is the answer to the question. Okay, easy enough? Let's do one more. Was there one more maybe that you had a question about? Okay, now let's not get in the habit of not doing our homework reviews. All right, would you do this for me then? Let's get out our Christmas gift worksheet. Anybody have a question about that? to me, am I supposed to know how to do this? The answer is yes. You are
Yes.
supposed to know how to do all of this. So who had a question about something on the Christmas gift worksheet? What? It was your homework over break. It was called Christmas gift worksheet. It was on the website about 12 times and we talked about it a lot.
I didn't look at school.
You all have it. It's on in your small habit. So who did it had a question about something? Yes.
I saw that. Told me to get like
All right, let's look at number 3. Problem number 3. Here we go. A bicycle with a 24-inch diameter tire. Okay, so I'm going to go ahead and make that a 12-inch radius. 24-inch diameter would be a 12-inch radius. Is traveling at 8 miles per hour. How many revolutions does the tire make per minute? So I'm looking for RPMs. Revolutions per minute. Okay? Now, what?
That's circumference.
Yeah, how do I do it?
You find the circumference.
Okay, so what would the circumference be? The circumference of this wheel would be
2 pi r.
2 pi r, which would be 24 pi inches.
Yeah, correct.
Would everybody agree with that?
Yeah.
Okay, what did they do that for, Tom?
So then you know how long the entire wheel is.
How much ground it covers in
Yeah,
every
how much ground,
revolution.
yeah.
So Tom says this distance right here is the length of one revolution. Because if you think about it, all the way around this tire is 24 pi inches. So if it rolls one time, that's how much ground it will cover, right? So 24 pi inches is one revolution. All right, where do I go from here? We're getting some of the pieces gathered in. How do I start organizing this work? Well, let's start with 8 miles in 1 hour. That's the given, right?
Yep.
What do I want to eventually end up with?
RPM.
I want to end up with eventually with revolutions per minute, right? So I need to get rid of the hours. So what do I know about hours?
There's 60 minutes.
1 hour is 60 minutes. I'm going to run out of room here. Let's start over again. So I know that 1 hour is 60 minutes. Okay, now I've got my minutes. I'm good. Now I have to get from miles to revolutions, and what Tom did is the key. 1 revolution is 24 pi inches. Would you agree with that? Now, everything's hunky-dory, but miles and inches are a problem,
Oh, man.
right? So what could I do?
A lot of math.
Well, not a lot. How many, let's go miles to feet. How many feet in a mile?
I have no idea.
We should know this.
5,280.
5,280 feet in a mile. Okay. How many inches in a foot?
Well,
12 inches in 1 foot. All right, now let's look and see what we've got here. The miles canceled. The inches canceled. The feet canceled. What am I left with?
revolutions per minute.
Which is exactly what we wanted. This part right here is the tricky part. You've got to remember that a revolution is a circumference. That's the key. That's the key. Good work. Anybody else have something on your Christmas sheet that you forgot how to do? What I'd like you to do is look at the very next page in the packet. It's called Worksheet 4145. We have done everything on this sheet except for the very first problem, number 1. We haven't spent much time with that, so we need to spend a little more time with that. But first, I'm going to go through and do part of every problem to make sure that you're up to speed, because this is going to be your homework tonight, whatever we don't get done in class, okay? So let's look, and we're going to skip number 1 temporarily. Let's look at number 2. We're going to analyze the cotangent function. Now, what do you think is going to be the very first thing I'm going to do with this? I'm going to draw a picture of it. Of course I'm going to draw a picture of it. I want to draw a picture of it so I can see what it looks like, and maybe that will help me answer the questions. Does anybody remember what a cotangent looks like? Remember your lime green sheet? That's on there. Asymptote here on the axis, asymptote here at pi, and a decreasing function like Maggie said. This is my cotangent. What is its domain? Now, we got to be careful with this. These are a little complicated. I'll grant you that. Have I graphed the entire cotangent up here on the board? No, I only graphed one period of it. So it will continue on over and over again. Would you agree with that? So we're tempted to, and this way too, we're tempted to say the domain is all real numbers because it goes on forever and ever in both directions. What's the matter with that?
The asymptotes.
Because it's got asymptotes. So your domain is all real numbers except where the asymptotes are. Where are the asymptotes?
Pi, 2 pi.
Pi, 2 pi, 3 pi, and so on. So how could I express this? My domain is all real numbers, but x can't be what? If this is y equals cotangent x, x can't be what? Can't be pi, can't be 2 pi. What about negative pi?
Can't be that.
Can't be that either, so, I mean, this would be okay. I would accept that. We gotta put 0 in there too. But can you think of another way maybe of expressing that? Instead of like actually making a list, can you think of another way?
Could you write everything?
No, I don't want to do that. I don't want to write it. What?
What the domain is still.
X pi. How about let's use n instead of x since x is in our equation. X can't equal n pi, where n is some whole number.
Just saying the domain of what.
Let's say no, let's say an integer. Beautiful, Mr. Preston. Absolutely amazing. Good job. You're going to become a valued addition to this class. This is probably the best way to write it, but I would accept that. The idea is if you have an asymptote, you're not part of the domain. Okay? The only trig functions that are going to have all real numbers as their domain are the ones that don't have any asymptotes. What are the trig functions that don't have asymptotes? Sine and cosine. That's it. Sine and cosine. Everything else has asymptotes. So you're going to have a situation like this with every trig function except sine and cosine. Good. How about the range? Look at your picture. All real numbers. Your range is all real numbers. It goes up, up, up forever and down, down, down forever. Your range is all real numbers. Very good. How about continuity? If you drew the entire cotangent curve, would you have to lift your pencil? Yes. When do you have to lift your pencil?
To get over that
To get over the asymptotes, that's right. So this is not continuous. This is not continuous. Each piece of it is, but the curve is the entire, all the pieces. Would you say this is an increasing or a decreasing function?
Decreasing.
Decreasing. Cotangent is decreasing. What about tangent?
Increasing.
Tangent is increasing, yeah. Cotangent is decreasing. Symmetry. Does this thing have any symmetry? And when I talk about symmetry, I'm talking about symmetry to the x-axis, y-axis, identity, or origin.
Yes. Yeah.
What symmetry do you think it has, Stephen?
I mean, if you cut it, yeah, never mind.
Well, you know what? I think if you think about this for a minute, I'd like you to imagine.
If you cut it down to 0, 0, the origin,
exactly.
everything on this side is going to be equal to everything.
I'd like you to think about flipping here, taking everything right here. Look at this, just this branch of the curve right here. Take this and fold it across the origin. Take this and fold it across the origin. This thing has symmetry about the origin. This is actually an odd function. It has symmetry about the origin. It does not have symmetry about the y-axis. If it did, it would look like this on this side. So there's no symmetry about the y-axis. Asymptotes, we already talked about that. Would you say this thing is bounded above, below, both, neither, what? Bounded above? No bound. It's not bounded above or below, guys. It just goes up and down forever and ever. Does it have any maximums or minimums? No, it doesn't. All right, look at number 3. Now you're going to sketch. Pick one. I'm going to do one for you. The rest of them you have to do on your own. We're going to talk about all that other stuff too. But number 1, or number 3, A, B, or C? C. C? All right, let's do C. Okay, we kind of already talked about this a little bit. How will we start this? How will we start this, folks? We'll make a draw. A sine curve. I'm going to hold this for the end. I'm going to wait on that guy. Too much going on here. I can't keep track of all of it. Harry, I almost liked it better when you were asleep.
Well, he took my calculator.
No,
That's very irresponsible of
he
him.
just planted it on me.
Okay.
How would I plan it? That's
Okay, we're focused on cosine.
All right, thank you. We're going to graph a sine curve. What does this 1/3 here tell me? No, it doesn't tell me the period.
1/3 tells you how tall it
It
is.
tells me how tall it is. It has to do with the amplitude. It tells me how tall it is. Now remember, I'm not doing this. I'm just going to erase it for a minute so there's no confusion. I'm graphing this right here first. So I've just graphed my handy-dandy sine curve. There's no coefficient here. What does that mean?
Means
You don't
2
divide
pi.
the
The
period.
period just stays the same, so what's the period? 2 pi. This is just everything's just normal about it. Now that's my sine curve. So now how do I turn that into a cosecant? We already talked about it. Drop in asymptotes. So I'm going to put in an asymptote every time I cross the x-axis. There's 3 of them. And then I'll take this guy and flip him up. And this guy and flip him down. And of course I've got the magic of the board, so I'm going to go ahead and erase this sine curve. That is this. Everybody with me? But the problem had a +1 on the end of it.
So you have
What
to
does that do?
the shift it
That takes every point
back 1,
and does what with it?
goes back 1.
Doesn't go back 1. That's not in parentheses. That's going to go up 1. So it's going to go up 1. So now I'm going to be up here at 4/3.
I was saying no.
And this is going to come all the way up to what? Where's this going to come up to? 2/3. So the red thing is the answer to the question. And now we have to fill in amplitude, period, frequency, phase shift, or horizontal shift. This can, sometimes we call this phase shift, sometimes we call it horizontal shift. It doesn't matter, it's the same thing. And vertical shift. So can you fill in any of those?
Vertical shift.
We're talking about the red curve now, the red curve. Vertical shift is 1. You can either write 1 or you can say up 1.
Asymptotes at 0, pi, 2.
Okay, asymptotes are not a question, that's amplitude. That's amplitude. What's the amplitude? Actually, there isn't any amplitude. Because by definition, amplitude is half the distance from the top to the bottom. Look at the red curve. Does it have a top and a bottom? No. Now, is the 1/3 an important number in the problem? Absolutely it is in terms of graphing, but it is not the amplitude. If this had been a sine curve, it would be the amplitude. But secants, cosecants, tans, and cotans do not have amplitude. Good. How about period? Now, help me. Have we talked about frequency? I can't remember.
Yeah.
Frequency is simply the reciprocal of the period. So if we have a period of 2 pi, our frequency will be 1/2 pi. Now, I want to caution you, when you write this, make sure it looks like this. Don't be doing this kind of stuff, because when you write it that way, it looks like ½ pi, which is a different thing altogether. Write it 1/2 pi. Frequency simply means it's the number of periods you get in an interval 1 unit long. So let me just pause for a minute. Well, actually, let's finish this and then I'll talk about frequency a little bit. How about a horizontal shift or phase shift? Does this problem have any shift horizontally? The only way horizontal shifts happen is if you had something like this. That would make a horizontal shift, wouldn't it? We didn't have that. Let me just quickly give you a little rundown. I'm going to erase this. Anybody have a question about this picture? You okay with it? Okay. Let's just show you real quickly. You don't even need to write this down, but just so you have a grasp of what frequency is. If we had a sine curve that looked like this.
Wait.
If we had a sine curve that looked like this, what would you say its period is? Half, right? Its frequency then, according to what I just told you, should be 2/1 or 2. And it is, because frequency is how many periods you get in an interval 1 unit long. So if I look at 1 unit of length, how many periods get accomplished? 2. That's the frequency. If you had a sine curve that looked like this, what's the period of that curve? 2. Its frequency is a half, because in 1 unit you only get half a period done. All right, we'll finish this tomorrow. Your homework is finish that worksheet except part 1. You don't have to do part 1. Have a good day.
Okay. So, okay, people want straight down.
I'm pretty sure people will straight down.
Worst, go to worst.
Nothing
Could be worse.
I have that theology.
I thought it was.
Why would you do that? The final report going to go theology or?
Hey, what do you have?
We're going to study. Aren't you
Are you kidding me? You don't like this
Take good
situation?
notes and try to
What's wrong with it?